Hello, John Levesque here again. This is the second video in a series of 6 videos. In the first video, we actually used PerfTools Lite on the VH1 application, which is an astrophysics code developed at North Carolina State University, and we produced some very interesting data. What I'd like to do in this video is relay that information to the application itself. Okay, in this video I'm going to try to use 2 windows into the system. In the upper window, I am going to look at the PerfTools Lite output, which is at the end of this output file. Remember that this is the output from the application itself, and then we start with some profiles here. Now in the bottom window, remember I mentioned during the build that the option on the compiler, the -h list equal A, would generate an annotated listing of a particular routine. For example, parabola uses most of the time, so it makes sense to look at that. So we will VI parabola. Alright. Now, parabola is not too big. You notice that it has several... Oh, I used the wrong file. Instead of using the .f90 file, I'm going to use the LST file. Okay, let's make the window a little bigger for a minute here. On this listing file, you notice you get a lot of information on what was actually transferred to the compiler. It was running our compiling for Broadwell, and these are all libraries that were passed to the compiler, which are all defaults. Now, one of the things that's interesting here is this legend. When we start looking at the actual code, this legend is going to tell us what the compiler did with the input code. Could have been vectorized, may have unrolled. Unwound is when a loop is explicit, like 1 to 4, and then it basically eliminates the loop and has 4 iterations. Okay, so we can refer to that legend as we look. Now here it's saying that this do loop is in fact vectorized and unrolled by 2. So the R means unrolled. Now this second loop is, it might be a little confusing here. This loop is not fused with that loop. It's fused with the loop after. So these two are fused, basically saying that the compiler replaced these 2 loops with one loop that encompassed these 3 statements. The reason the compiler did not fuse these 2 loops is because the loop bounds are different. Okay. Alright, now if we go down, here is a loop that's vectorized, and it's all by itself. then another loop that is vectorized, unrolled by 2, and then fused. In fact, all the rest of the loops are fused down below. Notice that we do get some verbiage here that tells us, restates what the compiler did with those loops. Okay. So, here is, here parabola is using most of the time, and everything vectorizes. So, let's look at the line numbers. And what this is saying is line 45 here. This is using 2.3% of all of the total time of the program. It is a little bit load imbalanced, 14.1%. And so, but it is vectorized. So what gives with that? Now, one thing that is not very good with this particular routine is that while the compiler is fusing, like for instance these last 4 or 5 loops, it doesn't eliminate arrays or demote arrays. In other words, notice that if these are fused, in other words, if all these loops, these 4 loops are made into one, then these arrays could be scalars. There's no reason to make them into arrays. And the fact that they are arrays is really increasing the required memory bandwidth. So one of the optimizations that we should consider here, which would be very good, is to manually fuse these loops and eliminate the arrays that we can. For example, all of these search 1, 2, 3. Also, delta AA is used here, and no, I take that back. I'm sorry. Delta AA is returned, and so all right. But there are several arrays that can be demoted to scalars. All right, now as far as these up here, it's actually pretty difficult to fuse these loops, and it's because you have to pretty much stay ahead. And in other words, notice that this is using n-1, so it's using this this very first value of diff A, and then also it's just, I've done it. You can merge these 3 loops, but the logic becomes a little complex. Okay, so let's go back and let's look at Riemann. All right, so to look at that, we need to edit the .lst file. All right, and here again we have the same preliminary information. And now let's see, what line number should we be looking at? Lines 77 and 78. Okay, notice that this is a nice vectorized loop, but this loop is not vectorized. And so 77 and 78 are in the same loop, so this really accounts for like 5% of the total runtime. It is not vectorized. And why isn't it? Well, if you look at this inner loop, you notice there's an exit outside of the loop. That's not good. And besides, this is the loop over the mesh. So what this is actually doing is for each zone, it is actually going through a calculation of the pressure, and then it's trying to converge. It's basically doing a iteration to converge to a constant pressure. And once it gets the convergence less than tall, it exits. So this doesn't vectorize, that doesn't vectorize. Whenever you don't see a V, that means it doesn't vectorize. Now we should also look down here in 63. Now this is a night message. This is not vectorized for an unspecified reason. And then this one says a recursion was found on pmid. So pmid here is set and then used. So this is a problem. Now, the solution is actually fairly straightforward. Let's say we want to vectorize on L. We basically want to pull L inside of the end loop. Now, in order to do that, we need to introduce an array. Let's make it a logical array that is basically converged. So initially, we will set all the elements sub L equal to false. In other words, it has not converged. And then, for the first iteration, we'll go through all these calculations. We won't do this exit. What we'll do here is we'll say that converged equal true here for that L. All right. And then, after we get out of the first pass of L, if L is on the inside here, it's going to be executed 12 times. After we get through the first pass, we'll check to see if all of the elements of converged are true. If they are true, then we can exit. And now we come back, if not all of them have converged, and we should probably have an if around all these statements saying, if not converged, then we do this calculation. Because we don't want to keep on calculating if something has converged. All right, and so we can go through this. Actually, I have done this. It actually runs very well. The problem with doing the vectorization that I discussed is you're basically, if you have a few zones that do not converge for small numbers of n, then you're going to do a lot of unnecessary computation. But the thing is that if you vectorize, you're going to run 4 to 5 times faster. So you can afford doing some additional calculation. If you want to see the rewritten, go to my website, and there's a book there that actually discusses this vectorization. Okay, so that's looking at the vectorization characteristics, let's kind of look and see why are we using so much MPI time here. Well, it turns out that the algorithm used here, let's look at sweep Y, is actually doing 3 sweeps. And after each sweep, they have to do a MPI alt-all to transpose the data for the next sweep, so that we have all of the data that we need to do the sweep with on the node. And that's what this MPI alt-all, not on the node, but on the core. And so as you can see, there's an all-to-all. This is actually a triple nested loop. And it calls PPMLR, which let me show one last thing before we quit here. I am going to run a pat report, and I am going to ask for call tree plus source, and I'm going to apply it to this and put it out onto profile call tree. Alright, now let's look at profile call tree. Alright, let's make this window bigger. I really like this display. So basically what we have here is we have, this is the main program, and from line 237 it calls sweep Z. Sweep Z then calls an MPI all-to-all from here. So sweep Z has 2 calls to MPI all-to-all. And then sweep Z uses an additional 5.8% of the time outside of these all-to-alls. And part of that time is spent calling PPMLR. Okay, and it shows you the line numbers that this is called from. And so this gives you a very good idea of the computational sequence of the application. Let me do one more thing here. I don't particularly like this source thing here. I'd much rather do this. Whoop. Alright, so this takes out, this really I like a lot better, because notice you can see that VH1 calls sweep Z that contains MPI all-to-all. It also calls PPMLR. PPMLR calls remap, which calls parabola. And then remap uses this amount of time outside of everything it calls. Then Riemann is also called from PPMLR, and PPMLR calls parabola directly. So this is extremely useful if you're trying to figure out how the computation proceeds in this application. Okay, so that's the end of video 2. A little longer than I intended, but hopefully it was useful. Thank you for your time.